I've seen a lot of videos that'll explain GPUs versus CPUs, but just kind of do it as an analogy, like, oh, a GPU's like a lizard, but a CPU's like a bird or something. And I'm like, okay, like that doesn't help me. It's great for an investor. If you don't need to understand a GPU, that's great. But I'm someone who actually likes to understand what my computer's doing when I write code. So for me, I found this really annoying, which is why I went to Nvidia's website. I read their white pages, I read their documentations, and now I think I have a decent understanding of how GPUs work. So I'm going to share that with you guys today. Before we get into hardware, let's talk a little bit about the software that GPUs are designed to support so we know why they're useful. Basically, what a GPU does is it does a lot of parallel computation really fast. So if you have a number, you keep doubling it, and you need the result of the previous doubled number before you get the next one. Like you start with 6 and you double it, you get 12, you double 12, you get 24. If you started with 6, you can't start to double 12 until you know that double 6 is 12. So you've got to compute things sequentially. However, let's say you have a for loop where you're doing something on an array at each index, and each index is independent of all other indexes, then you can just work on that index specifically and all the other indexes simultaneously. That is parallel computing. That's something a GPU is good for, which is mainly computer graphics. That's the big first thing. However, a lot of people don't realize that scientific computing, data analysis, those kinds of things have been done on GPUs almost since GPUs were invented. Nvidia's been aware of this and been trying to support people doing these kinds of things since GPUs were invented. So GPUs aren't just graphics units, despite what some people think. On a single CPU, you'll have multiple cores, and each core is capable of doing a bunch of stuff. It has a bunch of different supports for different operating system things that are required for a computer to work, as handling for input and output devices. It has handling for loading and storing to memory. It's just basically a single core is an entire computer. It's not just a binary calculator. It can do a lot of different activities. When writing code, you can make a thing called a thread, which is basically saying, on the CPU core, I want you to run these instructions, and it's a process for that CPU core. And you can make multiple threads. So if your machine has 24 cores, you can make 24 threads. And if the operating system lets you, they'll all run at the same time. They'll do a really good job, and your program will finish way faster than if it was just on one single core. However, if you make 1,000 threads, which is the first beginner mistake everyone makes, you see what a thread is, you're like, oh, so if I make 1,000 threads 1,000 times faster, that's not actually going to help, because you only get like 24 cores on a CPU, so it's not going to be that much faster. The point of a GPU is basically to say, what if making 1,000 threads actually was helpful? Because we just have so many cores, but you can't do that on a CPU, because if you make a CPU with 1,000 cores, you're just gonna have a $1 million CPU. But if you make the cores really cheap, inexpensive, and weak, then you can print up a bunch of cores, many thousands of cores, for not a lot of money. The way programming on a GPU works is you write a thing called a kernel. It's not related to operating system kernels, at least as far as I can tell. What it is it's just a code for a GPU. It gets sent to the GPU, and it says, okay, you got these two arrays, I want you to access both of them, and for each element, I want you to add it. And the kernel will just say, add these two at whatever index. Each thread will get assigned an index, and it'll make a bunch of threads, thousands and thousands of threads, and it'll just spread them across the whole GPU and do it really fast. But how does it actually do that? First, what the GPU does is it creates a bunch of threads. It arranges these threads into groups of 32 called warps. These warps are arranged into blocks, which are also usually groups of 32, and these blocks are arranged into grids. Every block in a grid, every thread in a grid is going to run the exact same kernel. However, the GPU can be running multiple grids at the same time, as long as both of those grids require the same features of memory. It can't run two grids on two completely separate memories that require different arrays, but if you need the same memory for two different grids, it should be able to. In simpler terms, if I wanted to do two computations on the same array, then I'd probably be able to run both those kernels at the same time. But if I wanted to, say, load Minecraft graphics and Valorant graphics, and those are two completely different processes that are both filling up the entire VRAM on the GPU, those probably won't have kernels running at the same time. This is where most of the deep but not actually deep explanations tend to stop, because it's what you need to kind of understand what a CUDA kernel is. So let's dive deeper. Graphics cards have their own onboard memory, and they also have a GPU, which is a chip that does the actual computations on the graphics card, and we're going to divide it into a bunch of different subsections. Every GPU has one gigathread engine, which basically just has one function. This sends blocks of threads to these units called streaming multiprocessors, or SMs, which are basically the core of actual GPU computation. So remember, block has a bunch of warps. Warps have 32 threads. Usually a block will have 32 warps. So a single streaming multiprocessor at one time is most likely handling 1024 threads or more. Let's say that we're working on the array summing problem, and for simplicity, let's just say we're using an array of length 1024. So each one of the threads in the block takes its own index, loads the element in array A at that index, the element in array B at that index, sums them together, and stores that into memory in array C. Let's pass these to the SM and see how it's actually going to do these computations. First of all, inside the SM, you have a few different sections. You have CUDA cores, you have load store units, and you have special function units. These are the three sections that'll actually execute some kind of instruction. On the Fermi architecture, which we're going to use because it's simpler and easy to understand for a single SM, you're going to have 32 CUDA cores, 16 load store units, and 4 special function units. CUDA cores do basic operations that you learn in day 2 of programming: addition, multiplication, subtraction, bit shifting, logic, those kinds of things. They're very simple, very basic, just like calculators, not even full computers. Load store units, on the other hand, are handling memory management side of computing. So a load store unit can load variables from memory and store variables into memory. And what these actually can do, which is pretty cool, is they can load multiple things into multiple registers at the same time. So even though there's only 16 of them, if you align your memory properly and do everything right, then you should be able to load multiple things at the same time. The special function units handle harder math problems, which include things like trigonometry, square roots, and weirdly enough, floating point division also falls into this category, which if you know how it works, you should be, oh, that makes sense. If you don't, you should be, really? But anyways, floating point division, trigonometry, square roots and stuff, that all falls under special function units. In very low-level computing, instead of using variables, you tend to use things called registers, which are just what your actual operations will act on. So if you do division, addition, multiplication, bit shifting, whatever in assembly, you'll know you add 2 registers together. And on a normal CPU in the modern day, you might get up to 100 registers. On an older CPU, you might have 8. On an Nvidia Fermi architecture, which is an old architecture, the register for your CUDA core special function units and load store units, which all share the same registers on a single SM, will have 32,000 32-bit registers. That's a lot of registers. So when a block reaches an SM, the instructions of that block go into the instruction cache. These instructions are divided up by warp, so one unit would be warp 1, instruction 1, warp 2, instruction 4, warp 17, instruction 38, or whatever it is, that's a unit. There's 2 warp schedulers which try to pull instructions from the instruction cache that can be ran at the same time. So let's say warp 1, instruction 2, all the instructions numbers are the same because all the warps are running the same kernel. But let's say that instruction 1 requires CUDA cores, instruction 2 requires load store units. So warp 1's already done its instruction 1, it's on instruction 2. So the first warp scheduler might say, the next cycle, we're doing warp 1, instruction 2, we're gonna load stuff. Whereas the second one might say, warp 2 hasn't done its instruction 1 yet, so we're gonna do warp 2, instruction 1 on the CUDA cores while you load in things. And then there's 2 dispatch units, one for each warp scheduler. The first dispatch unit will say, okay, we're doing warp 1, instruction 2, which is loading, go to the load store units and do this. The second one will say, okay, we're doing warp 2, instruction 1, which is a CUDA core operation, go to the CUDA cores and do this. SMs also have their own cache, which for an L1 cache, 64 KB, which is its size, sounds like kind of a lot until you remember that it's about half the size of the register file. Then you're like, what's even the point? But it's there if you want it. Let's walk through a few steps of our array adding algorithm and how it would run on this SM so that you can understand it even better if you don't already. First, let's load the data for warp 1. Now, a single load store unit can load up to 4 32-bit floats on this architecture at one time. So that would mean that in theory, we could load all 64 numbers to do warp 1's additions in just one way through the load store units, but that would require a lot of good memory alignment and a lot of things that need to go right that probably won't happen. So that it'll probably take 2 cycles, but just for the simplicity of the example, let's say we get it in 1 cycle. This means that the second cycle, warp 1 and warp 2, will have different instructions that are next for them to do. So warp 1 could do all its additions while warp 2 loads in all of its data. And in the next cycle, warp 2 can do its additions while, let's say, warp 17 loads in its data. Then warp 17 can do its additions while warp 4 loads in its data. And maybe it takes 2 cycles or even 4 cycles to load in all the data, depending on how your memory's aligned and how exactly your kernels wrote. And in that case, there would be off cycles where one warp's loading data and no additions are happening. But in theory, it would still be really parallelized because even if only loading is happening, that's still 32 threads of memory loading happening at the same time. Most calculations and algorithms will also require more complex algorithms, like, oh, you got to do a couple bit shifts on a memory. You're usually not loading 2 things from memory and only using them once in one add with each other and then storing something else to memory. So it's pretty rare that you wouldn't be able to parallelize even further and actually have your CUDA cores being backed up, being the thing weighing down on your algorithm, not the load store units or the special function units. So if we were to take a modern CPU, 24 core CPU from Intel and say, all right, I'm gonna run the same algorithm, and we were to take the arrays and we were to add them in multiple threads across all the cores, you'd have less cores, you'd be able to do some weird tricks with loading and storing, but you wouldn't be able to load and store while you're also doing computations. So at the end of the day, there's way too many assumptions that get into the way of saying which one would actually be faster. Probably the CPU, but on a GPU, there's 16 SMs on the Fermi architecture. On a modern day 5090, there's 170 SMs, and they're like these SMs times 4. They're way more strong. They basically look like 4 SMs in one SM, so they get a lot stronger. So it's not that an SM itself is a powerful computational unit. It is, but not relative to a CPU. What it is a ton of SMs make really strong parallelization for things that can be very easily parallelized, like a neural network forward pass or video game graphics computations. So why do CPUs even exist anymore? Like, what's the point? Why haven't we just converted to running all our operating systems on GPUs? Well, first of all, CPUs are really good at doing sequential tasks that aren't parallelizable. So if you have, say, you want to keep incrementing a number, add 1 to a number, then take that sum, add 1, or anything where the start of the next step requires the output of the previous step every single time, there's no parallelization, then you're gonna need a CPU, because a GPU, there's no point. You make what, 32 threads, 31 of them are if false stop, and then one of them is actually doing the computations, then you're just using something that's a lot weaker than a CPU, because one CUDA core, load store unit, and special function unit is worse than a CPU core, objectively. Also, there's a lot of higher level abstractions like operating systems permissions and different things like that that seem like they're software, but are actually requiring really specific hardware things, registers, flags, permission, just intricate little details that don't exist at all on a GPU. You could not run a modern operating system on a GPU at all. It just wouldn't work. GPUs are really good at their specific set of tasks, but really bad at general computing. They cannot do operating systems. A single CUDA core is not going to be very powerful when it comes to running a sequential task that has no parallelization. CPUs are stronger for that. GPUs are stronger for things in parallel. So now hopefully you see where the analogies come from and you can understand it a bit better when you make your LinkedIn post and someone comments why. Now, if you made it this far and you're thinking to yourself, wow, this guy seems really cool. I wish he had a YouTube channel I could subscribe to. Well, good news. I do. You're watching it right now. Click subscribe. Thanks for watching.